In this video, we will cover plastic and elastic deformation. This includes definitions of plastic and elastic deformation, the position on the stress-strain diagram, and provide illustration of how several types of materials behave under both elastic and plastic deformation. Understanding plastic and elastic deformation is of key importance in material science and engineering because these principles determine how a material deforms under loading and unloading. Before we define elastic and plastic deformation, let's define stress and strain as they quantify deformation. Stress is a force applied over an area or a pressure force. Strain is the change in length in the direction of load, a stretching or a compression. In this video, we will deform three materials by applying a bending moment through the material. However, deformation can be tensional, pulling the material axially, compressional, compressing the material axially, or torsional, applying an axial moment. Elastic deformation is a non-permanent deformation. This means the material will deform under an applied load. However, when the load is removed, the material will return to its original shape. In elastic deformation under loading, the bonds between the individual atoms in the lattice are stretched, allowing the material to deform. When the force is removed, the bonds and also the material return to the original shape. On the stress-strain diagram, in the elastic deformation region, the region of stress-strain plot corresponding to elastic deformation is linear. The slope of this line is known as the modulus of elasticity. This provides the equation stress equals modulus of elasticity times strain. The point on the graph where the deformation shifts from elastic to plastic is called the yield point. The yield strength is the stress that is required to cause plastic deformation. By convention, we define plastic deformation as a permanent strain of over 0.2%. In plastic deformation, when a load is applied to a material, it deforms. However, in plastic deformation, it does not return to its original shape. This is due to microscopic dislocations, such as edge and screw dislocations. When these dislocations are introduced into a lattice, they permanently alter the structure of that lattice. Thus, a plastic deformation is a permanent deformation. In the plastic portion of the stress-strain diagram, the curve is not linear. When the stress passes the yield point, the material starts to deform much more rapidly. Unloading is, however, linear and has the same slope as the elastic portion of the plot. This allows a material to be strain hardened because subsequent loading will follow the same line as the previous unloading. This allows the material to undergo more stress before it starts to deform plastically.